Hey guys, thanks for joining me. This is part 3 of my investigation into the Florida pedestrian bridge collapse. And in this video, I'll be looking at the member 11 that collapsed and looking specifically at the forces that were in that member and looking at the capacity of that member and comparing the two, comparing the capacity of the member and comparing that versus the actual forces that were in that member prior to collapse. And so I'll be doing some quick calculations, and I'm going to try to keep it interesting, and we are going to be looking at some equations and numbers. So it's just part of the process of doing a thorough investigation to make sure we're not just putting a theory out there that's not really going to hold up. So in order to support my theory that I've put out there, these calculations are essential, and without the calculations to back up theory, it's really not gonna hold water, and it'll prove fruitless. So let's get started here. So member 11 we know failed, and we know that member was in compression. We also know that the bridge weight was approximately 950 tons. So, looking at the bridge here on this rough sketch here, we know that the bridge weighed 950 tons. So, assuming the bridge is approximately equally weighed across its span, that the reaction at each end support, so this would be at each pier that the bridge had been resting on, is approximately 950 kips. 950 kips is 950,000 pounds. We use the term kip to represent 1,000 pounds. So 1 kip is 1,000 pounds. It just makes our numbers smaller. Instead of writing everything out in pounds, where it would look, the numbers would be much longer, we cut out 3 decimal points and we have a smaller number. So 950,000 pounds is what each support was seeing approximately. So again, 950 ton bridge, 950 tons is 1,900 kips. 1,900 kips divided evenly between 2 supports is 950 kips at each support. Alright, so we know that. Now, that's the self-weight of the bridge at each support, the reaction at each support. Now, at the support adjacent to member 11, we now need to figure out the geometry of the member and find out the angle of the member so that we can calculate the force from the bridge self-weight that's in the member. Now, looking at this, these dimensions I got off of the drawings on the online of the bridge. We know the bridge height approximately 15 feet. We know the length from this point where the diagonal meets the top of the canopy to the bottom of the diagonal at the support is approximately 20 feet. So if I take these two numbers and I do some basic geometry, opposite over adjacent, we're looking at tangent, opposite over adjacent, we get a value of 37 degrees approximately. So the angle of the member with the horizontal is approximately 37 degrees. Okay? Now, in order to figure out the force in the member, this is a very basic principle here. Sum of the forces in the vertical direction must equal 0. So that's that equation. Sum of forces in the vertical direction is 0. So in order for that to be the case, the vertical component of this member must equal 950 kips. So that equation will look something like the force in member 11 times the sine of 37 degrees equals 950 kips. Stay with me, guys. I don't want to bore you with numbers, but this is key, because I can't support my theory without proving it to you with calculations. So these calculations aren't that difficult, so stick with me. All right, so that's the equation. This is the force in member 11, the axial force. All right, so that's this force right here. All right, and we have to find its vertical component to that equals that, and that vertical component has to equal 950 kb. This is a basic statics equation. Sum of vertical forces equals 0, and sum of horizontal forces equals 0. In this case, we're only worried about the vertical force from this diagonal. This member right here is really not contributing to resisting the reaction, and so we don't consider this as a member in the truss. Really, it's really not part of the truss. This and this top horizontal canopy member are really not contributing to the truss system. All right, so if we look at this now, just going back to this equation, the force in member 11 is 950 kips over sine 37. Again, basic algebra here, just moving things to the side, to that side, one side of the equation to solve for force in number 11, and with that value we come up with approximately 1,580 kips. All right, so that 1,580 kips is the force in member 11 from the weight of the bridge. Okay, so we have that. So that is only the self-weight. Now, we know that the bridge had, that member had 2 post-tensioning bars. And those post-tensioning bars had a tension value of approximately 200 kips. And how do we know that? That's from the drawing on this table. That's this table on this drawing, and it showed. Now, it didn't show any force for member 11, but we know member 11 did have post-tensioning bars in it. All right, so I'm going to go off of the forces shown for member 2, which is, I don't know if it's showing up here, but that's 200 kips. Member 2 is the opposite diagonal member on the opposite side. It's the matching diagonal compression member on the opposite side of the bridge. All right, so we're going to say that 200 kips is what was the post-tensioning force in each bar within that diagonal member. So 200 kips, each bar is contributing, it's squeezing the member. We also know that we have 1,580 kips of compression due to the weight of the bridge. So the total compression in that member, total compression, is self-weight, 1,580 kips, plus the compression from the post-tensioning bars, which is 200 kips per bar. So, and we have 2 bars. So 2 bars times 200 kips per bar is 400. And that total now is 1,580 plus 400. That's 1,980 kips. All right. So that 1,980 kips is the actual force that member number 11 was seeing during when it was collapsed. Now that's what it's supposed to see, assuming these bars are tension to 200 kips. 1,580 kip force due to the self-weight of the bridge. That's an accurate number. That's accurate. This number is what we're questioning, and we're trying to find out how important this number is, because we know at the time of the collapse the contractor was stressing, he was tensioning the bars, and we need to find out if this number, how critical this number is to the compression within that member, to the actual capacity of the member. So we're going to compare this number now to the capacity of the member. This is what the member actually was supposed to experience, the total compression that it was supposed to actually see, and we're going to compare how much capacity that member has. And there's an easy way to calculate that number. The capacity of that member is basically the strength of the concrete mix times the area of the cross section, all right, with some reduction factors that are incorporated. So we know that the area of the member, it's a rectangular shape, 21 inches by 24 inches rectangle. 21 inches times 24 inches is 500 square inches. So that's approximately the cross-sectional area of the diagonal truss member. From the drawings online, the concrete used for the truss was 8,500 psi concrete, which is a high-strength concrete. 8,500 psi is the concrete strength. We're going to take that and multiply it by 500 square inches, and that's going to give us the approximate capacity of the rectangle shape. So in this case, the capacity is 8,500 psi. Pardon my writing here. I'm trying to write and look through a small screen at the same time. But 8,500 psi times 500 square inches equals 4,284 kips. So 8,500 psi is equivalent to 8.5 ksi, which is kips per square inch, and we're multiplying that by 500 square inches, and we're getting 4,284 kips. So that's at best, the capacity of, that's the highest capacity that member could see. Now, when you're doing a design of a member, you have to reduce this number to account for, to give yourself a safety factor, all right? You can't just take that number and compare it to what the actual what the member is going to see, because that would be a perfect situation where everything was perfect, that the concrete was poured perfectly, that there were no voids or material defects. This is a number that you're never going to design for. So you have to reduce it to account for flaws and imperfections, and just, you have to give yourself a safety factor. So with a concrete column, the safety factor, there's a bunch of factors. Now these factors I'm getting from the concrete code. There's a factor of safety for the concrete. You actually reduce the strength of the concrete by 15%. You also, because of the rectangular shape of the member, you reduce, you add another 30% reduction to account for the rectangular shape of the member, and then there's also another reduction factor for the possibility of a eccentricity, which I discussed in part 2. Things actually not, like your axial, your force that you're applying to the member being off center, so you have a moment that's being created. Now, if you add all those safety factors, they're all multiplied and incorporated into this equation. So your safety factors are approximately, you have a 0.85 for concrete, and then you take that and you multiply it by 0.80 for eccentricity. So again, that's a 15% reduction, that's a 20% reduction, and then you take a 0.7, that's a 30% reduction. So if you take all those and you multiply them out, you get approximately a 48% reduction in capacity from the perfect condition, I'll call it. This is what I would say would be ultimate. This would be the highest that you could ever see. But when you're doing design, you can't take that value. You have to reduce it to account for imperfections, as I stated earlier. So if you take 4,284 kips and multiply it out and reduce it by 48%, you get 4,284 by 48%, so 0.48. That is approximately 21 make sure I'm right here, 21, 25 kips or so. I'm sure you guys will correct my math if I'm wrong. I'm looking at my previous numbers here, and I think that's about right. So 2125 kips now is what, if I'm doing a design of this member, 2125 is my capacity. I cannot exceed 2125 in my total compression due to self-weight live load and post-tensioning. So 2125 is higher than 1980. So that's good, right? I have a capacity of 2125, and I have a self-weight and a post-tensioning compression of total of 1980. So I have my difference, 2125 from 1980. I have a 145 kip surplus. So 145 kips. If I were to add more than 145 kips to my compression force into my member, I would be exceeding my capacity at that point, and then I would actually fail my design So what I think happened, what I think could have happened, that's really not a big, that's not a lot of margin for error here, right? We're looking at about 5% margin of error, but difference between this number and this number, about 5%, between 5 and 7 or 8%. So what could have happened is if the contractor had not been properly post-tensioning these bars. So we know based on the drawings that he was supposed to go to about 200 kips. Now these bars, they are 1 3/4 inch diameter, and a 1 3/4 inch diameter bar can actually be stressed up to a tension of 400 kips approximately. So each bar can actually go up to 400 kips, and we're at 200 kips. So if I take one bar and I stress it to, instead of 200, if I tension it to 350, I'm going to exceed my capacity. If I add another 150 kips to that, I'm exceeding my capacity. So at that point, my design isn't working. All right, so as you can see, there's really not a lot of safety factor. There's not a lot of room for error in my post-tensioning. So if the contractor exceeded this 200 kips and he made it up to 350 kips on just one bar, he's exceeding the capacity of that member. And I think that's what may have happened. And again, as I discussed previously, if these two bars are not tensioned equally, if I have 350 kips of tension here and 200 kips of tension here, I have an uneven stressing of the member. So that uneven stressing creates a bending moment into that member. When you have a compression member that's also seeing a bending, that member, the amount of compression that it sees is reduced, as opposed to a member that has no bending and is only seeing compression. So a member in pure compression can see, in this case, can see a total capacity of 2125, but when I add compression and a bending moment, this 2125 capacity is reduced. And again, but this reduction, if I have a moment, that reduction varies based on how much moment I'm applying. So the bigger the difference in forces of these two post-tensioning bars, the larger my moment, the more reduction in my capacity of the truss member. So bottom line, what's the takeaway? The takeaway is, if everything were perfect and these post-tensioning bars were stressed perfectly the way that it's shown on the drawings, and the concrete material was correctly used, there were no defects in the concrete, and what I'm showing here is that the design is adequate. But if the contractor deviated at all in his post-tensioning, you take away your safety factor, and now you could potentially violate your the design as it was intended to, as the bridge was intended to be built. So I think what happened, and I'm proving it here, that the contractor in his post-tensioning, he exceeded this 200 kip tension that the drawings were showing, at least the preliminary drawings show. Again, I just want to clarify, the drawings that I'm basing my findings on are the ones on the internet. They're not the drawings that were actually used in construction of the bridge. They're preliminary drawings submitted in the bid proposal by the design build company. The firms that were involved with the construction, they did not actually put their as-built drawings online yet. So we don't really know what was done during construction. But if, assuming everything is similar, construction was similar to what's shown in these drawings, those are my conclusions. And I think it's pretty accurate. I think, and based on what happened, how the bridge collapsed while the contractor was out there tensioning a bar, or both bars, that he exceeded this capacity of the member, this 2125 capacity. Now, 2125 capacity is a design capacity. In reality, you can go above this. You can still go above this member probably and be okay, because there's a lot of safety factor involved, and it's very, very, very unusual for any construction in a existing structure or a new structure to have a member fail. Where bridge failures typically occur is at details, at connections, at changes in the cross section. That's where a member typically fails. So in this case, a failure, I would expect to see a failure at like a connection here. This is where things come together. It's very unusual for a member to just fail from just straight on being overstressed. Usually a failure in a bridge occurs where you have things coming together. In this case, though, it looks as if that member had been overstressed by incorrect post-tensioning of the 1 3/4 inch diameter bars that go from end to end of the member. And again, as mentioned previously, it's unfortunate because it looks to me that this was not a necessary step at the time of failure. The bridge member was in compression. There's no debate. There's no debate to that. If that member was having cracks in it, as discussed previously, those cracks occurred during transport. The cracks that were there with the bridge in its final position were not a safety hazard, and that's what the FIG engineer stated in his phone call to the state. The cracks in a tension at this location in a compression member are not going to grow. The cracks, because the member's in compression, are stable. They will not grow wider because they're being squeezed, and in reality, the cracks would potentially get smaller in width, and they were not a safety issue. So I agree. As an engineer, if I had been the engineer, I would have made the same call. I would have said those cracks are not significant, not a safety issue. Yeah, we don't like the cracks. The cracks, we have to figure out why they were there. Maybe why they were, when did they occur? But we don't really need to worry about them because if they're in this compression member, they're not going to grow. All right. So these are my conclusions. Again, looks like between capacity of the member versus forces that were in the member, actually in the member, that the design is sufficient as presented. However, any contractor mistake in post-tensioning reduces your margin of your error, your margin of error for error, your safety factor is reduced, and as stated, there's really not a significant room for error in the post-tensioning procedure before you overstress the member and exceed its capacity. So, hope that's been informative. Really appreciate you guys checking in, watching part 3. Any comments, please put them below in the comments section. I appreciate all your feedback. Any challenges to my theories, I appreciate any alternative theories you guys come up with. Always interesting to hear, and I hope to hear from you. And thanks for watching. Take care. Bye.